Good morning. This is the 16th lecture of our AS and A-level chemistry lecture series. Okay. And the last lecture, this is 15th lecture, we were talking about the gaseous state of matter and finished our lecture with two problems, solving two problems. The third problem is one of the problems generally in AS and A-level exam, multiple choice question. This, I'm taking another example here. It says, which one of the following gives the correct value of the relative molecular mass of gas? And then there are four choices. We have to select one correct one. And the problem is this: we have been given a volume of a flask, and in this flask we have a gas of about 4.19 gram. And the pressure of the flask is 300 kilopascal, and the temperature is 20 degrees Celsius. And the gas constant is given there. And then we are asked to find out the relative molecular mass of the gas. Well, you know that we said to find out or solve the problems in this ideal gas equation, we have to always rewrite the gas equation according to the question. So here the question is we have to find out relative molecular mass of the gas. And relative molecular mass is designated by mR, and this is equal to, if number of moles is equal to mass of the gas divided by relative molecular mass. So if we rearrange the ideal gas equation, the molecular mass, relative molecular mass is equal to mass of the gas, gas constant, temperature in Kelvin divided by pressure and volume. So we have pressure, volume, gas constant, temperature, etc. Now we go for this four solution. Which one is correct? Well, if we start looking at the temperature and volume, pressure, etc. And in right unit also. Do not forget to give the right unit of the parameter. So we have 4.19 gram of gas. So we know mass of the gas is 4.19. Here is 4.19. And then we have a relative, gas constant. Gas constant is given there. And then we have temperature. Temperature is given as 20 degrees Celsius. We must have to remember that the temperature unit should be in Kelvin. And we know how the Kelvin is converted into Celsius, or Celsius into Kelvin. So to convert Celsius into Kelvin, we have to add 273 degree Kelvin. So here it is then converted into Kelvin. Temperature is converted into Kelvin. So we see mass, gas constant, temperature is over there. Then we have to see what is left with given value. And we know that pressure is given, and pressure is given in kilopascal. So here it is kilopascal, 300 kilopascal. If we convert it to pascal, it is 300 into 10 to the power 6. And the volume is given here. So this is the volume. Volume is given here. It seems that this here we have taken all the right parameter with right unit. And if we look to this one, well, here is temperature in Celsius, so it cannot be the solution. If we go to this one, we see that here it is, the pressure is given in kilopascal. We cannot keep pressure in kilopascal. It should be pascal. So this one should not be correct either. If we go here, we see that this pressure and volume is up and divided by this other parameter. This cannot be. So the only correct solution is A, and rest are not correct. Well, we finished the discussion of the states of matter, gaseous state in details as per syllabus of AS level. Now we are talking about liquid state. Well, when we apply heat energy to a solid, what happens then? The molecules in the solid start vibrating vigorously. And then force of attraction becomes weakened. And then the solid changes to its liquid state at its melting point. This is what we call melting state. Now question comes, what is melting point of a solid? Well, if a solid changes to liquid in an atmospheric temperature, the temperature at which it changes to liquid is the melting point of the solid. Well, we talked about ionic, multiple covalent bond, metallic bond, van der Waals forces in our lecture of 10th and 11th lecture. And therefore, depending on this type of bond, we have many different types of solid and with having a wide range of melting point. When we freeze a liquid, what happens? That means when we cool a liquid, immediately the molecules loses its kinetic energy and increasing force of attraction, and then stop sliding each other, and at sufficiently low temperature, the liquid solidifies. We call this state freezing state. Now we want to talk about two terms, vaporization and vapor pressure. When we heat a liquid, what happens then? Molecules start moving faster in the liquid, and the force of attraction of molecules becomes weakened, and then the liquid start evaporating. Well, at a certain temperature, it start boiling when we heat liquid. What is boiling temperature then? We say again, the boiling temperature of a liquid is temperature which a gaseous state converted into the liquid state converted into gaseous state at 1 atmosphere. And here I have also given a conversion factor of atmosphere and Pascal. If we say a more exact definition of boiling point, what do you say? The liquid at which the vapor pressure is equal to the atmospheric pressure. This is what is a more exact definition of boiling point of a liquid. I want to clarify that 1 atmosphere is equal to 101,325 Pascal pressure. Now, next slide. We would like to explain vaporization and vapor pressure. Well, here we can see that this is water, liquid water. So, water molecules move from liquid to vapor. You can see that it is moving from liquid to vapor. And the more and more it moves from liquid to vapor, we see that some of them come back as a liquid also. And there in C, we have an equilibrium where molecules going from liquid to vapor at the same rate as it comes from vapor to liquid. So this is we call vaporization, the change from liquid state to the gaseous state. The energy required for 1 mole of liquid to change to 1 mole of gas is called the vaporization or enthalpy changes of vaporization. When we cool a vapor, it loses kinetic energy, increasing force of attraction. At sufficiently low temperature, the gas liquefies. So the term we have been discussing now, this change is called condensation. The terms we have been discussing now is melting, freezing, vaporization, condensation. These are all reversible processes. So here we show at equilibrium what happened. The concentration of water molecules in the vapor remains constant. That is equilibrium between the water molecules in liquid state and water molecules in vapor state. This is what is done. So that's what we have to know. And the vapor pressure is caused due to the molecule hitting the container of the valve, and as the vapor pressure increases as we increase the temperature. Next slide, we go to solid state. We have been talking about this solid state in bonding a little bit with details, but in here we know that in solid state what happens, atoms are held tightly together and the shape, it is got a definite shape. And the distance between molecules are small compared to liquid and gas state. The atoms in solid, they vibrate in its own position. As the temperature increases, the vibrational movement increases. Depending on chemical bonding, we say that we have classified ionic, covalent, and metallic solids. Other than these solids, we do have polymeric solids and nanomaterial solids. One more thing, that we have to classify solids in broad classification, amorphous and crystalline solids. Well, I said amorphous. It means that three-dimensionally the molecules in solids are not arranged regularly. It is randomly arranged. And then crystalline solid, the three-dimensional arrangement are very regular. Almost all solid materials we can have in both amorphous state and crystalline state. Almost all. A few examples of ionic, covalent, and metallic solids we mentioned in our A-level lecture, specifically 10th and 12th lecture. And another few I have to mention that, we have millions of crystals we do get in nature, and also we can synthesize it. But then these millions of crystals must belong to one of the 7 crystal systems which we can establish mathematically. These 7 crystal systems are cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. Okay, we have to determine, we always are talking about three-dimensional regular arrangement. So we have to determine the three-dimensional structure of solids. And there we need this technique, X-ray, electron, and neutron diffraction techniques. These are the 3 techniques which are really used to determine three-dimensional structure of solid. And it means the three-dimensional means that we have to determine the position of atoms in the internal structure of the solids. The 7 crystal systems are defined in few parameters. I again say that in A level or OS level, you need not to know all about these crystal systems and their definition, etc. Here, not only the pyramidal definition is given, it should be also symmetric. So these are all details which you read in undergraduate classes and last semester of undergraduate classes. Just to mention about cubic, we say this is a three-dimensional axial parameters, 6 parameters, A, B, C, alpha, beta, gamma, and with these parameters we are defining cubic, where all the 3 axes are equal and all the 3 angles are 90 degrees, rhombohedral, all the 3 axes are equal, and then all the angles are equal but not 90 degrees. Hexagonal, A is equal to B and B is not equal to C. And alpha, beta, gamma, alpha, beta 90 degree, gamma 120 degree. Tetragonal, A is equal to B, B and not equal to C, alpha, beta, gamma 90 degree. Orthorhombic, all axial parameters are not equal to each other, but all axial angles are equal to 90 degree. Monoclinic, all axial parameters are not equal to each other, and alpha and gamma is equal to 90 degree, beta is greater than 90 degree or not equal to 90 degree. Triclinic, none of the parameters are equal to each other and no angle are equal to 90 degree. So with this, we can also discuss one or two examples of crystalline solids. For example, most common one is sodium chloride, that means table salt. You can see here the arrangement of chloride ion and sodium ion. And this is a close packing arrangement. That is, the chloride ion and sodium ion are touching each other. To see it a bit enlarged, we have taken this, right? The small one, this yellow one, is sodium, and the bigger one, that is this one, is chloride ion. You can see here, this sodium ion is surrounded by 6 chloride ion. Yeah. So this is called a sodium chloride octahedron. Similarly, if we go to a chloride ion here, you see this one bonded with sodium. This one is bonded with sodium, and then sodium. So each chloride ion is bonded with 6 sodium ion, and each sodium ion is bonded with 6 chloride ion in the unit cell. That's what is shown. Yeah, this is what we can take about magnesium oxide. If we just replace the chloride ion to oxide ion and sodium ion to magnesium ion, we will see that the same structure is for sodium chloride and magnesium chloride. Just we are replacing them. So these two are called isomorphous compound. That means two compounds when have similar structure, they are called isomorphous. And then we talk about metals and alloys. A pure metal, we have been discussing in our previous lecture that it has the close packing arrangement of layers of close packing. We say A layers, and then in top of this B layer, and then in top 3-dimensional, if we go top of this, either A layer or C layer. If that depends on whether it is cubic close packing or hexagonal close packing. What I want to show here, that if we apply a force to a pure metal, the layers can slide to each other because of this force. But when we have an alloy is nothing but a mixture of 2 or more metals. We take an example, brass. Brass is an alloy of copper and zinc. So if we apply force to a brass alloy, then we will see that layers cannot be slide very easily. For that, generally, alloy are much stronger than that of pure metal. Oh, well, with this slide, probably we finish the today's lecture. That we call about, if we remember that we were talking about giant covalent structure, giant molecular structure, that is 3-dimensional network with building on 3-dimensional network and huge structure. For example, we take carbon. You see, in carbon we can have more allotropes, but we discuss only 2 allotropes here, and these 2 allotropes are diamond and graphite. So again, we call element in definite element having 2 or more forms in different structure. We call these forms allotropes of that element. So carbon has more allotropes, but we are talking about only 2. One is a diamond, which is a cubic structure, and the graphite is a hexagonal structure. This is the graphite structure, you see. Each carbon atom is being attached to another 3 carbon atom, and forming a layer of carbon atoms here. And then the second layer of carbon atoms, again, having a weak bond between this first layer carbon atom and second layer carbon atoms. And therefore, this is sliding each other, etc., and a little bit softer than that of diamond. How the diamond is organized here, you see that every carbon atom is attached with 4 carbon atoms, and then it is 3-dimensionally extended. And therefore, diamond having a much more stronger structure than that of graphite. So these two are allotropes of carbon. When we have compound having more form, a same compound having different crystal structure, we call those compounds as polymorphs. As we are calling isomorphs, that means the different compounds having same structure. Here, same compounds having different crystal structure, we call them polymorphs. So you see, silicon dioxide has many polymorphs. One is quartz, another cristobalite, and then tridymite. So quartz is trigonal in crystal structure. Cristobalite is cubic in crystal structure. Tridymite is hexagonal crystal structure. We are showing one of these structure, that is silicon dioxide, and it is quartz structure. Here you can see that every oxygen is this one, silicon is the smaller one. All silicon is bonded with 4 oxygen. Each silicon is bonded with 4 oxygen. Each silicon is bonded to 4 oxygen, and then we can see take this one that bonded with oxygen, oxygen, and it almost like diamond structure. And here is the crystal of cristobalite. Quartz. This is the quartz crystal. Probably with this one, we finish the 16th lecture, and then we go for chemistry of group 1 and group 2 elements. And in the syllabus, you have to read chemistry of group 1 and group 2 as well as group 17. This will be our next lecture, the 17th lecture. Thank you very much for your attention.